Let's look at some examples. Let's try to multiply matrix A to matrix B. Both matrices are of dimension 2 by 2. So the product A times B is going to be, what's its dimension? It's also going to be 2 by 2. The inner dimensions match each other so that the product can be defined. And the element of A times B on the first row and first column is going to be the scalar product of the first row of A and the first column of B, which is 1 times -3 plus 2 times 1. So it's -3 plus 2, which is -1. The element on the first row and second column is going to be the scalar product of this first row and the second column of B, which is 1 times 2 plus 2 times -2. So it's 2 minus 4, which is -2. And then the element on the second row and second column is going to be the scalar product, the second row of A, and the first column of B. So it's 2 times -3 plus 3 times 1, which is -6 plus 3, which is -3. And the last element, the element on the second row and second column, is going to be the scalar product of the second row and the second column, which is 4 minus 6, which is -2. You can calculate with the same definition that matrix B multiplying matrix A is going to be -3, 1, 2, -2 multiplying matrix A, 1, 2, 2, 3. And its first column is going to be, the first element is this first row multiplying this first column, which is 1, and the second element is the second row of B multiplying the first column, the second column of A, and it's -3. Similarly, you can find the second column to be 0 and -4. You can see that the product A times B is a different matrix from the product B times A. This is generally true for most matrices. The order of multiplication cannot be switched for matrices. The multiplication of two scalars. If we multiply two scalars, for example, 2 times 3, it is exactly equal to 3 times 2. But such is not the case for matrices. There are some special matrices where A times B might be equal to B times A, but those are special matrices. And in general, we have an inequality sign here.